Gradient descent finds the nearest valley. The nearest valley might be a shallow ditch, the real valley is on the other side of a ridge. Part 2 is about escaping ditches and fitting complex models. The terrain has many valleys. Gradient descent rolls into the nearest one and stops. That's a local minimum. Global minimum, the deepest valley might be far away, separated by ridges. In neural networks, local minima are everywhere. In pharmacokinetic models with nonlinear dynamics, the loss landscape is rugged. Finding the global optimum is not guaranteed by any gradient method. What if the biker occasionally rides uphill on purpose? Simulated annealing borrows from metallurgy. Heat a metal and it shakes loose from rigid crystal structures. Cool it slowly and it settles into the lowest energy state. The algorithm starts hot, frequently accepting uphill moves to escape ditches. As it cools, it becomes more selective, eventually only accepting downhill moves. The cooling schedule controls the trade-off: cool too fast and you freeze in a ditch. Cool too slow and you waste time wandering. If this sounds like the night market's parallel tempering, it should. Both use temperature to control exploration. What if you can't fill the slope? Some functions aren't differentiable. Nelder-Mead uses 3 riders forming a triangle, a simplex. At each step, the worst rider reflects through the centroid of the other 2. If the new position is better, the triangle moves toward the valley. If not, the triangle shrinks. No gradient needed, just function evaluations. In biology, Nelder-Mead is used for fitting models where the gradient is unavailable or unreliable, complex simulation models, discrete event systems, and black box objective functions. In pharmacometrics, the terrain has a special structure: population models with random effects. Each patient is a valley, and you need to find the population-level valley that accounts for all individual valleys simultaneously. FOCEi first-order conditional estimation with interaction is NONMEM's workhorse. It linearizes the individual models and iterates. Some stochastic approximation expectation maximization is more modern. It samples individual parameters and converges more reliably for complex nonlinear models. If you're fitting population PC models, these are the 2 methods you encounter. When to use which? If you're near the answer, you have good initial estimates from prior studies or physiological knowledge, use a local method. Gradient descent or Nelder-Mead will find the exact bottom quickly. If you have no idea where the answer is, a new model, unfamiliar parameters, use a global method. Simulated annealing, differential evolution, or particle swarm to find the right neighborhood first. Then switch to a local method for precision. A hybrid approach, global for exploration, local for exploitation. This is how most production calibration pipelines work. 6 strategies for the mountain biker. Gradient descent for the basic downhill ride. Learning rate for gear selection. Grid and random search for the cold start. Simulated annealing for escaping ditches. Nelder-Mead when you can't feel the slope. SAEM and FOCEi for the pharma-specific terrain. Know the landscape, pick the rider, and always check if your valley is the deepest one.